this problem is asking you to determine if the formulas are correct. Now, you don't have any names. The names are not important because you're not seeing if the name matches the formula. You're seeing if this formula is even reasonable. And here's how you're going to approach this. First of all, recognize that all of these are ionic. They're all ionic because they all have a cation that's a metal, and something is also ionic if the cation is ammonium, but none of them are. They all have a metal, so they're ionic. Metal is the first part. Sodium, potassium, in this order, is potassium, sodium, lithium, aluminum, and calcium. It's really important that you look at the periodic table, or are able to look at the periodic table, and to determine what the standard charge is for a particular family. So for this first family, the entire first family here is going to be plus 1, also known as the first group. So that's going to be your hydrogen and your lithium and all the way down. They tend to have a plus 1 charge when they're ions. And then the second family, or the second group, is going to be your plus 2 stuff. And that's going to start off with beryllium and go all the way down. We're really not worried about the transition metals here. None of these in this particular example problem are transition metals, because transition metals are going to require that they have the Roman numerals, right? So if it were, for example, iron, iron might be an iron 2 ion. It could also be an iron 3 ion. If you were to express it as an ion, it'd be Fe2 plus for iron 2 and Fe3 plus for iron 3. But luckily, we're not even concerned about transition metals or those variable oxidation states. You do need to be able to look at it and see the basics though. So the first family, plus 1. Second family, plus 2. Jump across the D block and you'll come up again with plus 3, typically. And that's going to include aluminum, by the way. So that's the main one in in this area of the periodic table. The main one you have to recognize is that aluminum is plus 3. And then we are not really worried about the carbon family. I mean, that one tends to form covalent bonds. So picking up again, nitrogen tends to be in the minus 3 group. So as an ion, it'd be called nitride. Nitride is N3 minus. Beneath nitrogen is phosphorus, which also follows the same pattern of being 3 minus. That'd be called the phosphide ion. Next door to nitrogen is the oxygen family, which tends to have minus 2 charge. And then next door to that, you have the halogens, which you definitely need to know is minus 1. So that's fluorine, chlorine, bromine. And then you don't really worry about the noble gases here. So all of these ions are in blue, and there's going to be some others, but those are like the key ones. Those are the ones that are going to have standard charges that you do need to recognize. Also, we'll put iodine. So know that chloride, minus 1. Bromide, minus 1. Oxide, minus 2. Just know that. And also know that you have hydrogen, lithium, all those things in group 1, plus 1. With that being known, you can actually solve for all of these based on the charges that they should have, and recognizing that each one of these compounds should be neutral overall, which means that your negatives and your positives should balance out. So let's take a look at the first one, see if it's valid. The first one, I'll tell you the name afterwards, but you don't need to know the names. But this is K3N. So here's how you can analyze these. Look, write out K3N and then split it apart into the ions. There are 3 potassium ions, and there's just 1 nitrogen ion in this formula. And I'm just writing 3.K. That just tells me it's 3 times the potassium ion. You can also do the same thing for nitrogen if you like. So what's going on here? Well, first you need to actually put the charges. Potassium is in the family that always has a plus 1 charge. Nitrogen is in the family that always has a minus 3 charge. Or 3 minus, doesn't matter. So just count. At this point, you see that there's 3 potassiums, which means 3 times positive is positive 3. And then over here, there's just 1 nitride ion, but every nitride ion naturally will have a minus 3 charge, which means that there's a total amount of charge of negative 3. Positive 3 and negative 3 are equal and opposite. Perfect. That is a valid formula because you just figured out that the ions do balance out numerically. Let's take a look at the next one. I'm going to shrink this down so that there's some room. Whoops, I didn't mean to shrink that. Let's see if I can do that again. Okay. So if I do the same thing with the NaS, so Na and S. This is the compound, or what might be a valid or invalid compound. So let's check it to see what it is. Split it apart into the two pieces. You have one sulfide ion in this formula. You also have just one sodium ion. Now fill in the charges. Sodium has a +1 charge because it's in the family that has a +1 charge. And sulfur, as an ion, is sulfide, is in the -2 charge family. That's going to be -2. Now, if you do your math here, you see that the total amount of negative charge is in this formula is a -2, and the total amount of positive charge in this formula is just a +1. Now, those are not equal and opposite, so there's no way that this compound could be neutral. Therefore, this answer is incorrect. It's not valid. Now, this question says which of the following formulas are incorrect. The second one is incorrect. If this sodium sulfide compound were correct in terms of the subscripts, it would be Na2S. And here's why. So if you look at Na2S, which is what it should be if it were written correctly, then you look at it this way. There are two sodium ions. There is just one sulfide ion. And then if you do your math, you get to see that a -2 from the negative side is equally balanced by a +2 from the cation side, or the positive side. And that would be the formula that would be correct. So, moving along with that same logic, you can do all the rest of them. I'll tell you now that, let's see, lithium is +1, oxygen's -2. So 2 + 1s is +2. A single -2 is -2. +2 and -2 are equal and opposite. Therefore, that is also a valid formula. So we have two valid formulas so far. If you look at AlF2 and do the same logic, I'll just write it out quickly. A single aluminum, so that's one aluminum, should have will have a 3+ charge. We saw that earlier. And this formula has two fluorines, so there's two fluoride ions, and every fluoride ion naturally will have a -1 charge, and the numbers just don't check out. You have a -2 from the negative side and a +3 from the positive side. This is not a valid formula, so you'd also select that one. And I'll just tell you that the last one is valid because you have a +2 from the calcium and a -2 in total from those two iodides. This next one is a little more involved because this is a percent composition type of problem that also relates to empirical formulas. As a quick review, the empirical formula is the lowest whole number ratio of the subscripts, which is going to tell you for a molecular compound how many actual atoms are in every molecule. For example, glucose has a formula of C6H12O6. That's a simple sugar. 6 and 12 are both divisible by 6. So if you divide them all by 6, you get the empirical formula of CH2O. And the empirical formula just tells you the relative ratio of everything. The empirical formula just says there's twice as many hydrogens as there are carbon and oxygens for every molecule. But from the empirical formula, you don't know without extra information what the actual molecular formula is. So this is the molecular formula. I will show an example of how two different molecular formulas or more can have the same empirical formula. Here's another sugar. Another sugar is C5H10O5, which is ribose, I believe. And that actually has the same empirical formula. They're not the same molecule, they're not the same sugar, but they have the same empirical formula, which means they have the same ratio of hydrogens to carbons to oxygens. So for number 13, it says a compound of nitrogen and oxygen is analyzed and a sample weighing 1.587 grams is found to contain this much nitrogen and this much oxygen. What is the empirical formula of the compound? So this seems like it's a lot of steps because it kind of is, but I'm going to show you the full way, which might be a little, some parts might seem like, why are you doing it this way logically? But this is because these types of questions can take lots of forms. Sometimes they'll give you the percent compositions. Sometimes they'll give you masses that aren't, they don't look like nice numbers. This process works for, this always works for finding the empirical formula, even if you're given information somewhere in the middle of the process. So the very first step we're going to do is step one, which says find the percent composition for each element. So to do that, I'm going to color code each of these two elements. So we have nitrogen and oxygen. Let's deal with nitrogen first. The percent of nitrogen in this compound is going to be found by finding the mass of nitrogen divided by the mass of the entire compound. And then the whole compound has a mass of this, which is 1.587 grams. So there's some amount of nitrogen here. Of course, just think always about proportions, fractions, percentages, and ratios. Those are going to get you through. And when you do this, you're going to oftentimes use percentages as fractional or decimal numbers, which is okay. Just be very comfortable going back and forth. You know that if you have a fraction, a decimal number, multiply by 100 to get a percent and go back and forth. So when you see a percent or you see a decimal number, be very comfortable going back and forth. So to do this, I'm going to divide the top number by the bottom number. So 0.483, I'm going to divide that by 1.587, and I get a fractional amount that is 0.3043. I can turn that into a percentage just because sometimes it just looks prettier that way. And that means that this is 30.43% nitrogen. That same logic is going to apply for finding oxygen's percent. So oxygen's percent is going to be, is that the right orange? There we go. So oxygen's percent is going to be a little different. First of all you got to do is replace N with O for oxygen. Replace the mass so that all fits. So for oxygen, it is actually a lot more than that. Let's do this. So for oxygen, it's going to be 1.104 grams of O. The mass of the entire sample is the same. And then you're going to have a different number. But that makes sense because oxygen is the rest. So sometimes you're not going to be given the other information. As a matter of fact, in this problem, your professor doesn't even have to give this part. If they give you the total mass of the sample, and they tell you that there's a certain mass of nitrogen or oxygen, you should be able to figure out the other amount. So just recognize that percentages have to add up to 100, and fractions have to add up to 1 when you're talking about totality here. So we actually are going to have, let's see, 0.6957 approximately with rounding. And that means that our percent is going to represent that as well. And that makes sense. Don't forget to change everything if you do copy things over. So we have these two percentages. That takes care of step one. Find the percent composition for each element. This is true. This percent composition is valid no matter how much of the sample there is. If you had 100 grams of this sample, so if the sample weren't this little bit, but it were 100 grams, but it were the same actual compound, then you'd have about 30.43 grams of nitrogen and about 69.57 grams of oxygen. And that's why this next step, I included it. So first, we don't really need this information anymore. So I'm going to get rid of it, save us on some space. Once you have the percent composition for every element, you are gonna move this down. Just save that information somewhere so we can shrink this and put it there. Helpful for us later. Now, the second step, take those percentages and turn them into grams. Pretend like it's a 100 gram sample because the law of definite proportions and all that other stuff, sometimes I forget. Those laws that you learn about related to compounds and elements and stuff. This says that, like I just said, no matter what the mass of the sample is, the ratio of the elements' masses are going to be the same. So a drop of water or an entire pool of water, it's still water. hydrogen and oxygen are still going to have the same proportion in each molecule. So that being said, let's just pretend like that 30.43% nitrogen is actually 30.43 grams of nitrogen. That allows you to work logically with both. We're also going to do that same molar conversions with the oxygen. So I'm really just doing molar conversions right now, 2 at a time though. So turning our grams of nitrogen into moles of nitrogen. The molar mass of nitrogen is 14.0 approximately. And the molar mass of an oxygen atom, so grams of oxygen to moles of oxygen, the molar mass of an oxygen atom is 16. I'm doing this without looking at the periodic table, so if I catch myself with a mistake, I will fix it. All right, and then that's actually going to be that second step. Just turn your, well, actually we kind of did 2 steps. We turned our percent into grams and then our grams into moles. So to do that first part, you're just going to divide, so let's see, 30.43, dividing that by 14, and you get 2.17. So you have 2.17 moles of nitrogen. And then here we would have, and this is just a mole ratio. So of course there's not actually 2.17 moles of nitrogen in this sample, but the mole to mole ratio between nitrogen and oxygen is what we care about. So for oxygen, it would be 69.57 divided by 16, and that's 4.35 moles of oxygen. So what you're going to do next is turn those moles, these numbers we just got, so these moles, is this step here, turn those into ugly subscripts. So I'm going to shrink all this information down because we don't really need it anymore either. And then I have this value and this value. I'm going to turn those into ugly subscripts. So it's going to be N with a small 2.17, and then we have O with a small 4.35. And this is starting to look like a chemical formula, but we know we don't see chemical formulas that look like this. We only have integers in the subscript position. So with that being said, divide both of these numbers, or if you have 3, like if it were say NO and carbon or something like that, no matter how many elements you have, this process will work. But divide those ugly subscripts by the smallest value. So I'll divide both by 2.17, and you will get something that's very close to an integer, or perhaps a half value or a third. In this case, it'll come out to be nearly an integer. And all that is going to give us the empirical formula, which is going to be NO2. And that's the empirical formula. If you were given the molar mass of the empirical formula, of the molecular formula, then you could convert. So this problem takes us to ugly to pretty. That gives us the EF. This problem technically could be extended. If you were given the molar mass of the molecular formula, which is the whole true actual molecule, then you would go from the empirical formula to the molecular formula. But this problem doesn't ask us to do all that. So that's why your answer is the first one. This last one, or this next one, is interesting because it's a combination of isotopes and ions. So for this one, you have to recognize the difference between isotopes and ions. I know the difference, but they're both I words, so even when I'm talking fast, sometimes I will say one and then mean the other, so sorry. But I'm very careful about it these days because the difference is very important, but they are both I words that are usually taught around the same time, so it's easy to get them mixed up. An isotope is going to depend on differing numbers of neutrons. So the key subatomic particle here is how the neutrons will change, which is a symbol for neutrons. For ions, the key subatomic particle is electrons, how they come and go. So this is an isotope of palladium. And here it is right here. So palladium has a mass number, in this case, this isotope of palladium has a mass number of 107. If you look on the periodic table for palladium, you'll see that you'll have a 46 and then you'll have 106.42 approximately. Remember that the integer value is the atomic number, and the atomic number tells you how many protons there are. Then you have the average or the weighted atomic mass for the isotopes of palladium that exist naturally. And it's going to be near, typically, the mass number for this particular isotope. So this isotope of palladium, if you were to kind of draw it out, so let's say you were to draw a palladium nucleus here, then you have all those rings of electrons, energy levels around it. In the palladium nucleus, it's gotta have 46 protons. That's literally what makes it palladium. If it doesn't have 46 protons, it's not palladium. This is denoted by the letter Z in those formulas. So let's see. I think it's just to put an X here. So if X is the formula for the atom, so that'd be PD in this case. That lower left number, which may or may not be there, in this case is actually absent, but that's going to be the atomic number, which is also known as the nuclear charge. It's how many protons are in the nucleus. It defines the symbol. In fact, that's why it's missing here, because you could put a 46. I actually recommend you do that. Just complete it. You won't always be given that lower number, which is the atomic number, but if you put it there, it makes the next step easier. So the first thing you should recognize is that because it's palladium, you look on the periodic table, it's gotta have 46 protons because that's what makes it palladium, and therefore anything without 46 protons is out. And of course, little like test taking strategies showed you that 46 protons make sense because 3 of the 5 options start with 46 protons. Another really, really common mistake is that people look at this isotope symbol and they think that 107 is the number of neutrons. That is not true. This 107 here, that's the mass number. And the mass number is a combination of the number of protons plus the number of neutrons. It's basically how heavy the atom or the isotope is. Electrons are really, 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 really light. They have like very negligible mass. But protons and neutrons are like 2,000 times heavier, so their masses are not negligible relative to each other. So the number of protons plus the number of neutrons is the mass number for that particular isotope. This palladium isotope is palladium 107, which is another way to write it. If you take the difference between the top number and the bottom number, that's going to tell you how many neutrons there are. So the difference between 107 and 46 is 61. So that's why this option also doesn't make sense, because this is going to trick people who think that there's 107 neutrons. The mass number is not the number of neutrons. So that's why it's 107 as a wrong answer for the number of neutrons. It would be too easy if that were the case. Now you're down to these two. So it comes down to looking at the electrons, right? Because that's the two things that differentiates these two options. And that's where you look at this part. The number of electrons is going to go up or down depending on if it's lost or gained electrons, which gives it a charge. So if something is neutral, remember that it has the same number of protons as electrons. But this is clearly not a neutral palladium. So it's an isotope because it has a certain number of neutrons relative to the other isotopes of palladium, sure. But now, when we are concerned with the ions, the ionic nature of it, so whether it has gained or lost electrons, that relates to electrons, of course, which are all around the edge. So if it were neutral, it would have 46 protons and 46 electrons. However, it has a 2 plus charge, which basically means that there's 2 more protons than electrons. That's the net charge. So if there are 46 protons and there's a 2 plus charge, there's got to be 2 more protons than electrons. So this particular isotope, or ion, and it's an isotope, but this particular species has just 44 electrons. It lost 2. And that kind of makes sense because if you think about it mathematically, you have 46 positives, add to that 44 negatives, which is the same as subtracting 44, right? So 46 positives tells you that there's 46 protons. 44 negatives would tell you that there are 44 electrons. And that tells you that there is a positive 2 net charge. Thinking backwards though, you don't know this part. So you're answering the question of how many electrons are there? And since you're answering the question of how many electrons are there, you just do your math here. If you were to subtract 2 from both sides, that's another way to solve it. That gives you that the number of electrons is equal to 44. So that's why this is your answer. It's really easy for people to think that there are 46 or maybe even 48. Just recognize that whenever something has a positive charge, it lost electrons. You're losing negative, which is the same as gaining positive, net positive. And if you have a negative charge in that position, then you're gaining electrons. For number 15, this question is asking us about density. So it's going to combine a little bit of your geometry knowledge with your density knowledge. This says osmium is among the densest metals with a density of 22.6 grams per cubic centimeter. Calculate the mass in grams of a sphere of osmium the size of a ping pong ball. You're given the diameter and you're given the volume of a sphere equation. First, recognize that density is mass divided by volume. The mass is not given. That's what you're determining. The volume also isn't given, but you can determine it because you have everything to complete it. Volume for a sphere is 4/3 pi r cubed. This question is not concerning itself with sig figs. We were given 3 sig figs. Pi can be 3 sig figs, 3.14, and all the answer choices are 3 sig figs. So don't worry about sig figs here. So we have the equation for density for a sphere, which is exactly this. Now you can algebraically rearrange it if you'd like to, or you can just plug in everything you want and move it around. I tend to like to rearrange things algebraically. So to solve for m, what I would do is I'd multiply both sides by the equation for the volume of a sphere. That gets rid of it in the denominator. And I don't want you to think that this capital D means diameter. This actually means density. To be a little fancier, you might see the symbol rho. Rho looks like a drunk P, but the Greek letter rho is really what you use for density. So I actually will make that substitution just in case you see that in your other STEM classes. So what we have here, and I'll make a note of that, density is this. I'm not using capital D right now simply because there's the word diameter here and that just might be a little bit much. But from high school, you should definitely remember that diameter is twice the radius. So if the diameter is equal to 4 centimeters, then the radius has got to be equal to 2 centimeters. So now you have everything you need to calculate the mass. Effectively, you have the volume here. We're multiplying that by the density, and that gives you the mass. So you can plug all that stuff in. It'd be pretty straightforward. I'll do it real quick. We have 4/3 of pi, so it's about 3.14159. The radius is 2, but we're going to cube that because we're getting volume. And don't forget we're multiplying that by the density. Always check your units. It's really important that you check your units. You have centimeters, so when you cube centimeters, you're going to get cubic centimeters. That is a third dimension, so it's a volume. You have grams, centimeters, good. Everything checks out here. But sometimes professors like to throw a curveball and they would give you the diameter in like millimeters or something like that. Just be very careful. So when you do all this math, you'll get your answer. For number 16, I'm going to get rid of all this. This one it's just really a stoichiometry problem. So I've already set it up. It says how many fluorine atoms are there in 14 grams of carbon tetrafluoride? And they were nice enough to give you the molar mass of carbon tetrafluoride. This one is a little bit tricky because you're determining how many atoms there are, so you know you're going to use Avogadro's number. It's going to be a crap load of atoms, right? A lot. But it's really easy to get the wrong answer because there's something sneaky and hidden here. First things first, you're going to start with the thing you know. You have 14 grams of carbon tetrafluoride. Convert that from grams of carbon tetrafluoride to moles of carbon tetrafluoride, using, of course, the molar mass as your conversion factor. So I could cancel out my units like this. Grams are gone, and I have moles of carbon tetrafluoride. Next, turn your moles of carbon tetrafluoride into moles of just the fluorine atom within the compound. So if you think about this kind of makes sense. This is just a ratio. For every 1 mole of carbon tetrafluoride, it makes sense that you'll have 4 moles of fluorine atoms, because if you look at the formula, there's a little 4 there. It's like boxes. Suppose that you have 3, actually, let me do it this way. Suppose you have a box. Every box has 1 shirt and 4 pairs of pants. That's a single box. You could think of that as like a molecule. So if you were to have 3 of these boxes, then you'll have 3 shirts and 12 pairs of pants. That's the same logic when it comes to think about how many atoms there are in a certain number of moles of something, or grams, or anything else like that. So that's where the 4 and the 1 come from in the orange. It's the ratio of the atom that you care about to the entire molecule. It effectively says for every 1 molecule of CF4, you have 4 atoms of fluorine. And then next, let's just get rid of those units. And then lastly, you're going to convert your moles of fluorine into atoms of fluorine using Avogadro's number. You cancel that out, and that makes sense. Your units are going to be this. When you do your math, you're going to get a big number. Unfortunately, all of these answers are big numbers, so you have to actually do your math here. Be very, very careful when you're using your calculator to do calculations like this, because it's easy to accidentally divide by Avogadro's number instead of multiplying. In which case, instead of an absurdly large number, as you should have when you're determining how many atoms there are in a reasonable sample, you might get an absurdly small number. So just be very careful when you're thinking logically about how your answers appear. Something else that's interesting about chemistry is that oftentimes there are multiple ways to solve something once you build a skills bank. So if you look at this question, it says the formula of the aluminum ore bauxite is Al2O3. What mass of aluminum would there be present in 185 grams of this compound? So kind of feeling like stoichiometry a little bit, and very similar to this one in some respects. You have a known mass of aluminum oxide, and you can turn that grams of aluminum oxide into moles of aluminum oxide using the molar mass. That's just a normal mole conversion from grams to moles. Then you could turn those moles of aluminum oxide into moles of just aluminum using the subscript ratio. So if you were to do the not really stoichiometry, but more so like the dimensional analysis, so to speak, you would see that it makes sense, just like we saw in the prior question. For every 1 package of Al2O3, every one of these Al2O3 packages has 2 aluminums in it. So it makes sense that you can go from moles of the whole thing to moles of just the one thing you care about inside that compound. And then you can go from moles to grams, using, of course, the molar mass. But just keep in mind you're using the molar mass for just aluminum there, because you care about just aluminum. So that's why the molar mass of just aluminum is whatever aluminum's average atomic mass is on the periodic table. Let me see what that is. I don't have that one memorized. That's about 26.98. That's one option. The second option is to recognize that this is kind of like a percent composition problem. So the way that you would do a percent composition problem, and I'd work this one out, is you just use the percent composition of aluminum in this whole compound and multiply it by the total mass of the compound. So here, let's see how this one would work. I'll shrink all of this down. There we go. All right, so let's go with the second option. The second option would look like this. You're going to use the percent composition of aluminum. So first you need to find the percent composition of aluminum in this compound. Percent composition is the mass of the element you care about in the compound divided by the mass of the whole compound. Entire compound. Now this is going to be related to this compound here. So the mass of aluminum we don't know per se, because that's what we're kind of figuring out, but percent mass is a ratio that's going to hold true for all amounts, all sample sizes of this compound, right? That's the logic here. So what we're really talking about here is molar masses for this compound of Al2O3. So let's replace these with values. There are 2 aluminums. That's really important that you recognize that. There are 2 aluminum atoms in this whole compound. So the mass of the aluminum is going to be dependent on the fact that there's 2 aluminums. But this is where you put the molar mass of a single aluminum, which is 26.98. I'm going to call it 27.0 grams per mole. So if you're wondering where this 2 came from, it came from the fact that there's 2 aluminums. This 27 is the molar mass of a single aluminum atom, but there's 2 of them, so that's why it's 2 times that amount. Now the molar mass of the entire compound is going to require, if it's not given, and it's not in this case, you got to do a little bit of math here, but the molar mass of the entire compound is the fact that there are 2 aluminums, which we literally just determined has a molar mass of about 27. But don't forget that there's also oxygen in the entire compound, and there's 3 of those. The molar mass of oxygen is 16.0 approximately. So you're just finding the ratio of aluminum to the whole compound in Al2O3. And don't forget, you can multiply that by 100 to get it as a percent. So what is the percent composition of aluminum and aluminum oxide? I'm going to work out this. So 2 times 27. And don't forget to divide that by all of that. So 2 times 27 plus 3 times 16. I got about 52.9% aluminum. That's step 1. Step 2 is you are going to do this, take this number and simply multiply it, because it's basically saying that if you have a 185 gram sample of the compound, 52.9% of that mass will be owed to just the aluminum in it. So it's going to be, now keep in mind, when you multiply with percentages, you got to turn them back into decimals. So it's 0.529 times the 185 grams for the whole compound. And I got 97.9 grams. So there's 97.9 grams of aluminum in a 185 gram sample of the compound it contains, or that contains it.